Hi everyone. So we will start the afternoon sessions of English chat of PyCon Hong Kong 2021. So the next sessions will be delivered by Barry Tam. His topic is applying ML machine learning models to cooling low predictions for higher energy efficiencies in buildings, a case study. So I pass the floor to Barry.
Hello, can you hear me?
Okay, Barry, you can share your slide. Yeah.
Okay, sure. So can you see my screen? Yes.
Yes.
Can you see the full screen, right?
Yep.
Okay, yeah. So if things all right, I can start now, right?
Yes. Yeah, you can start now. Thanks.
Okay, yeah. Thank you for inviting me to give a talk today. And on behalf of ETEL, I'm going to present you the topic of applying ML models to cooling load prediction for higher energy efficiency with a case study. So my name is Ben Tam, and I work as an R&D engineer at ETEL Building Services Engineering Limited, and I obtained the bachelor and MPhil degree in physics. Maybe there's some technical problem. Can you see me switching the slides? Yeah.
Yes, we can see that you
switch
the slide.
Yeah, sorry about that. Yeah. So I've done and I currently work on 3 projects. Just let me get at least one first. Yeah, here it is. I'm working on like chiller plant optimization and automated fault detection and diagnosis, AFDD, both of which are related to central air conditioning system. And I also work on data pipeline. And so today's rundown will be divided into 4 parts. First of all, I will give you a short introduction of central air conditioning system, and you will understand the basic component of a central AC system. And most importantly, you will know what is cooling load. And then we'll go to the second part to discuss why do we need cooling load predictions. And the third part, we will discuss our ML models. Finally, we will summarize our findings. So let's begin by understanding what is a central AC system. So in a central air conditioning system, you have something called chillers. So chillers are the equipment that responsible to cool down the whole building. So how does it work? Well, actually, there are water pipes passing through the chillers, and the chillers does their hard work to cool down the water, say down to 7 degrees Celsius. And this water will be pumped to different floors, represented by this rectangle here. And in each floor, you will have something called air handling units, air chillers. So just think of it as a fan. So you have cold water comes in, so cool down the air, and you switch on the fan, and therefore you have the cold air provided to the office, to your indoor space. And so that's basically air conditioning. And what's in return, the indoor heat is being absorbed by the cold water or chilled water. Say the temperature increased to 12 degrees Celsius. So this water goes back to the chillers, forming the closed loop water cycle. So basically, this part is the major component of the central air conditioning system. And of course, the chillers does a hard work, they generate loss of heat. They will be carried away by other equipment like cooling tower. But that's not the focus of today, so we just put it here for your interest. So if you think of the central air conditioning system in a higher level perspective, what it does is very much simple. So you provide electricity to the system, switch on the equipment. Then what it does is simply extracting the heat away from the indoor space and dump the heat to the surroundings. And so here I would like to introduce a keyword for you. that is the cooling load, which is the heat extraction rate. So by now, I hope that everyone would understand what is cooling load. It's simply the heat extraction rate from the indoor space. So then we go to the second part to discuss why do we need cooling load predictions. So we start by thinking a daily routine of an operator or a BMS or just a traditional program. And assuming that we have two chillers here, one have a larger cooling load capacity, one has a smaller one. So let's say the time now is 6 a.m. and you have to pre-cool the indoor space for the office hour, for example, 9 a.m. also. So which chillers should the operator or the BMS program to switch on for the office hours? That's the question he or she need to ask. And maybe he feels like today is hot or something. The cooling load may be large, like 1,500 kilowatts. So if you look at the figures on the right-hand side here, you have to switch on chiller 1 because chiller 2 failed to provide such a high cooling load. So let's switch on chiller 1 and see what happens. And the green lines are the actual cooling load being measured for the office hour is actually much lower than the operator expectation. So what's the consequence? Well, if we do some simple math here, let's say, assuming we have a chiller 1 operating at this cooling load, 1,200 kilowatts, then we obtain a rather naive model will obtain the 252 kilowatt power consumption for chiller. So, well, that's normal, right? So, but if we switch on chiller 2, what happens is that we actually obtain a much lower power consumption, just 184 kilowatts. So that means if you fail to predict the cooling load in certain accuracy, you switch on the wrong equipment, wrong chiller type, then you were generating the energy wasting control. And maybe some of you will complain, well, why do you assume this is a linear model? Well, this is just for illustrative purpose. In reality, we know that chiller power actually depends on other parameters here, like water temperature and flow rate and so on. So just for illustration purpose here, we demonstrate that the importance of cooling load predictions. So if we fail to predict cooling load accurately, we will switch on the incorrect chiller and generating and waste the energy. So if you still think it's a little bit complicated, let's do an analogy here. So let's assume cooling load is just a bunch of people here, and chiller is the vehicle type. So what is our task here is like predicting the number of people, and then we have to switch on or call a suitable type of vehicle to carry the people to certain destination. Let's say you predict that a bunch of people need to be carried to a certain destination. So what will you do? You call a tourist bus to carry like 10 or 20 people to some of the locations. But unfortunately, in reality, only few people shows up. Well, the tourist bus, of course, can still carry these people away, but what you are doing here is actually inefficient. What you should do, maybe you just call a smaller taxi, or in our case, in the cooling load prediction, just switch on a smaller chiller type. So by now, I hope that everyone would understand the importance of cooling load predictions. And then we will go to our main topic to discuss our cooling load prediction model. So let's first define our problem here. Our problem is to predict cooling load, say 9 a.m. to 10 a.m. and predicting the early morning, say 6 a.m. or 7 a.m. And we actually build the cooling load prediction models for grade A office buildings in Hong Kong. So how do we build our models? Well, we actually use several Python tools, such as Pandas, Seaborn for data visualization. And of course, the most important one is the scikit-learn to actually build a model. So typically, how do we build a model? Basically, just these 4 guys here. We curate the data, we clean it, we do some feature engineering, and then we build a model. So this is just a typical flow. But what I would like to emphasize is that data cleansing in our case is a little bit special. Most of us will just remove the missing data. If you're familiar with Pandas, that's just calling a drop NA method. And also remove some outliers noise, perhaps applying a moving average. And we also need to filtering out some non-stationary time series because some of the equipment would behave having a transient dynamics. So those data are not representative. So we have to remove them. And we also have to correct something called sensor bias because building data are not so accurate. So if we do not neglect these kind of bias or errors, those errors will propagate in our computation and our models would not be correct. We had a chance to publish the paper to energy and building, applying Bayesian method to find out the sensor bias. So if you're interested, you can refer to this link here. So let's begin by model version 1. So in model version 1, we decision trees ensembling together, each make its own prediction, and then we aggregate them to generate a final random forest, a final outcome here. That is our cooling law. So the first model, we have several features input for our model. That is the difference. We also have weather data. So we put it in, you feed it a few years ago. That's our result. What you're seeing here is the predicted cooling load by the model against the actual one. And the scatter point is square error with these values here. So if we put it into actual production environment and we run it, for example, in 2021, we obtain these figures here. So the bottom panel is the outdoor temperatures. You see there's a profile here. And on the top panel is a little bit difficult to read. I will guide you through. You have the blue lines here. This is the actual cooling loads. And the orange lines here is the predicted cooling load by model version 1. So it's mimicking the shape here, right? So if you also see some of the sometimes the cooling load is very low because those days are holidays. So our model captures it. But and you also see some kind of colored bars here, right? So what does that mean? If you would like to operate your system in certain cooling load range, say for example here, like the orange range, like 500 kilowatt to 750 kilowatts, what you will switch on is one large chiller. And if you would like to operate your system in this green range, you will switch on one large and one small chiller. So what I would like to highlight here, as the title suggests, P4, what is the problem, is that in this range, our model consistently prediction is consistently greater than the actual ones. So why is that? Because you look at the temperature here, there is a drop starting from 22 date, but it fails to adapt the change for the weather conditions. So it's sort of like mimicking the last week cooling load profile. So we overestimate our cooling load, and that would be energy inefficient. So why is that? If you look at the feature importance of the model version 1 here, what you are seeing is that the greater the value, the percentage here, the more weight the model will put onto that features. So most of the time, the feature will learn whether Sunday or holiday. But the second greatest part is the cooling load profile. It's learning the historical cooling load profile. And the final one is the weather. So we suspect maybe our model is learning too much from the historical cooling load. So we have to revise our features for our model. So let's go to the model version 2 here. So we do not change our ML algorithm, same random forest, but we have to completely remove our cooling load profile because maybe we think it is learning too much from it. And I will guide you through the rest of the features here. So the first one is the Sunday or public holiday, which also present in the model version 1, but I would like to give you a concrete example why it is a good feature. So what you are looking here is the cooling load against the outdoor air temperature. And you already see it is separated into two groups, depending on whether it's Sunday or holiday or whether it is a normal working days. So for the normal working days here, the cooling load actually increases with the outdoor air temperature. So pretty obvious because the hotter the day, you need more cooling load. to extract the heat from the office. So for the non-working day, the cooling load is low and it's not quite depends on temperature. So from these figures alone, you already see these guys here is a good features. And just a remark, so how do we know whether the certain day is Hong Kong holiday or not? We actually adopt a Python package called recommended. So if we focus more on the working day cooling load profiles here, you actually see quite a lot of vertical strips here. Even at fixed temperatures, outdoor temperatures, the cooling load varies a lot, right? For example, like 1,000 to 1,400 kilovolts. So the question remains is, what are the features contributing to such variations? So how do we do it? We actually fit these figures here using something called isotonic regressions, minus it by the actual cooling load, we obtain the residual. And residual is something that is not explained by the temperature. And we have to find out what other features contribute to such the residuals. And just a little bit details of what is isotonic regression is also provided by scikit-learn. You can go through it if you are interested. So the next slide here, we are showing the cooling load residual against the month here. What you are seeing is that this is a box plot here, in case you are not familiar with it. Box plot is visualizing the percentile of the data. So what I would like to draw your attention is the Q2, the median, the 50th percentile. What you can see that even though after we deduct the temperature contributions to the cooling load, we still see some modulations for different months. So this, from the data alone, we think that it maybe is a good feature for our model. And then we go to other part, that is the cooling load against the date of week. What we also see the median is also different for different weekday. For example, Monday has a larger median and Saturday has a lowest median. And finally, we also find something interesting here is that if this is a working day and it is after holiday, the cooling load is just slightly bit greater than the normal working days. So why is that? We provide an interpretation here. So in the holiday, you have cooling load, but it's very small from the previous slides you already know. But you still have some heat absorption from the surroundings, like the sun, the other external factors, external environments. So you obtain an inequality here. Your heat absorption is greater than the cooling load. So your office temperature would rise. And therefore you require more cooling load after the holidays. So we think that this is also a good kind of good feature, although the median difference is not quite large. So we put all these things in, the temperature and the days related features to our random forest and train it. So we apply the train test split from the scikit-learn to split our training set and test set with 30% test set. Then we train our model with something called hyperparameter search. You see here, we instantiate our random forest regressor and we put it in a grid search series, which is to perform some hyperparameter search. And then we also adopt the K-fold, which is used to split the training set from cross-validation set for training our model. And then we apply the dot fit to actually fit our random forest model. So we fit it, and that's the result here. You see that most of the feature importance, that is the most important part, is the outdoor temperatures as expected, and the rest of that is days-related features. So let's compare the model version 2 with model version 1. What you are looking at is, again, the predicted cooling load against the actual one. The points also scatter around y equals x. But what I would like to draw your attention is the root mean square error here. In fact, the model version 2 on average is a little bit less accurate than the model version 1, even whether it is training set or a test set. But our title suggest is still kind of preferable. Why is that? Now let's look back at the same figures here. Again, it's the June 2021. Blue line is the actual cooling load. Orange line is the predicted cooling load by model version 2. What I would like to highlight here is that in this part, you're seeing that the outdoor air temperature drops, and the model, the orange line, is able to capture such a change. And what you can see is that the predicted cooling load and the actual cooling load falls into the similar region, operating at the same chiller path. So our model version 2, even though it's on average is less accurate, but it is able to adapt to certain change in weather condition. So of course, we build a model that's POC. We have to deploy it to production environment. We actually apply these tools here. We have the advanced Python scheduler to schedule our job. We have Flask, and we also use some containerization technique, Docker and Kubernetes. And so this is just cooling load prediction, but how's our client benefits from our solutions? And in fact, cooling load prediction is just the one part of the whole solution. Cooling load prediction provide the values of cooling load, of course. And then we also have this guy here, that is the optimization. What it actually does a lot of hard work here to recommend the actual control to the BMS servers. That is you think of it as a server from the building. So for example, it will recommend which chillers to switch on. And of course, we also collect some of the real-time data to do the optimizations here. So what our clients can benefit is that with cooling load prediction, we are able to have a more energy efficient for the morning startup to pre-cool the office. And for the optimization part, we are able to recommend an energy saving control to the server. And at the same time, we have to maintain the chiller plant stability. So I will summarize the findings here. So the benefits for the clients, and of course we just highlight, is that our cooling load predictions make morning startup, that is to pre-cool the office, more energy efficient. And we just like to highlight some practical work on some ML models. So in fact, both accuracy and robustness are critical in commercial solution. You see model version 1 is accurate in model version 2 on average, but it fails to adapt a change in the weather conditions. So both accuracy and robustness are important. And second is about something called feature engineering. And feature availability is very important because you do a POC, you find the feature is good, but in production environment, those features might not available. So your model may not be able to put it into production. So we'd like to highlight these key points here. So when building a model, think about the production environment, whether those features inputs are available. And finally, we'd like to address the point about data cleansing. And because data are not so accurate in BMS or IoT data, especially sensor bias, we have something called sensor bias. So more on data cleansing is more important to just simply dig down to some of the advanced ML models. So basically, this is the talk for today. If you have any question, I will be very welcome to answer.
Thanks, Barry. So if you have any questions to Barry, so please raise your hands now. Or you can also type on the chat as well. So we will looking for any questions. Yeah. Okay, as I found one question on chat from John. So do you control the chillers for data center or telecom exchange?
By control, I think we are actually kind of like recommending the controls to the BMS, I mean to the client, so that they would know which chiller to switch on or switch off. And we actually have some sites, most of which are commercial buildings. Also, some of them are data centers.
So
and I also, yeah.
So Chris also asked, only use RMSE to weigh your model performance?
Well, actually, we this just show one of the metrics using our MSE, but of course, we previously also emphasized the importance, like whether the predicted cooling load and the actual cooling load falls into the same region of Cheetah pattern operation. We also use that metrics, that is whether the cooling load falls into the same Cheetah pattern operation for as our metrics. So we also apply having other measures to measure our performance. So just showing our MSE here.
Thanks, David. So any other questions? Yeah. Are there questions coming from VC? As mentioned, that sensors data is sparse and even unreliable. How may such case be discovered and tackled? Yeah.
Oh, well, actually, we are actually adopting something called Bayesian method to find out whether the sensor bias is very critical or not. And then we do some data cleansing on our data and finally build a model. So actually we apply some of course, we do some extra data analysis, the EDA first, and then we apply something called Bayesian method to find out the sensor bias.
Yeah. Thanks. So next questions from Christine Chen. Does it support all BMS bands?
Okay. Okay, so this is about kind of like integration work from software to the actual BMS program. So our surface is kind of like independent of the BMS brand. We actually deploy our surfaces to our servers on site, and then we actually do some integration work with the actual BMS program. So it's what should I say? It's independent of the BMS brands, our solutions. Yeah.
So a question from Tommy Cock, just for interest, does regional wind speed considered as a feature, as it may also affect the head transforming?
Well, yes, there's many kind of like weather conditions that contributing to our prediction model, but I would like to highlight is that again, that is the availability of the features. So most of the time, not all the features are available in the production environment. So have to think about these concerns when building the model. So that's why we didn't put most of the like wind or solar radiation to our production model. Yeah.
So we have 2 minutes left for these sessions. Yeah. So am I find at least 2 to 3 more question or message on the chat. So so bear with. Do you have any question you would like to answer on the chat? Yeah. You can select 1 or 2 from the chat. Yeah.
Okay, let me see. Okay, so LL does it considering the aging of equipment to make recommendation? Yes, that's actually a very good question. We actually do lots of hard work to find out whether the data are representative. And what you are mentioning is like the cheetahs or bumps are deteriorating. And we actually have some platform called FDD, fault detection and diagnosis, to find out whether the equipment are actually aging. And about your questions is whether we put it in to make our recommendations, we would sort of like retrain our model if we discover that the the equipment is actually aging, we retrain some of the model, not critical precision model, but some other models, and then we put it in to capture the reality of the chiller plants. Yeah.
Okay. Yeah. So thanks. Yeah. So
yeah.
do you have any? Yeah. So do you have any follow-ups on the message on the chat? Yeah.
Yes, Chris mentioned that why Model D is better than even if the RMSE is higher than model version 1. If you remember that, so model version 1 uses a features called historical Guadagno profile, which of course is mimicking the same, let's say the last week Guadagno profile. Of course, when the next week, if everything's all right, so the prediction will be very good. But when the weather changes, let's say from 30 degrees Celsius to, let's say, down to 25 degrees Celsius, then the model fails to predict that special event on that date, and it is sort of like commercially not quite acceptable. So RMSE is just, I would like to demonstrate that this is just as most of us would use these metrics to define whether a model is good or not, but in production environment or in commercial solutions, this is not the only criteria.
Okay. So thanks for Barry to give us a presentation today. Yeah. So we appreciate for that. So with you have so with the participants have any follow-up questions, you can contact with Barry. Yeah. So thanks again, Barry. Yeah.
Thank you.
So for the participants who asked a question, so maybe some of you doesn't use the registrations name just like Chris, LL. So it would be great if you can send me your registration name. So then you will have an opportunity to win a prize from our sponsors. Yeah. And then the VC, yeah. Okay, so screen sharing and okay. So the next session will be start from 2:45 by Kim Philo.